In this video, we're going to take a look at the electric field due to a continuous charge distribution. And a continuous charge distribution is different from point charges because with a point charge, the object, if you can even call it that, which is causing the electric field, has no physical dimensions. And so the field is very symmetric and very easy to understand. And by way of example, just as a visual, we have a point charge, which could be an electron, which is considered to be a dimensionless particle. It has an electric field which points radially inward. And then the counterexample to that would be what happens if you have a bar of charge, something which looks like that, or a line of charge, which might be a thin wire. With a continuous charge distribution, we run into some problems with utilizing Coulomb's law. Coulomb's law can readily be applied to a point charge, but Coulomb's law can't be applied directly to something which has got physical dimensions. And we're going to take a look at that in a minute. Now, one of the first questions you might ask yourself is, why concern ourselves, at least from a physics perspective, with a continuous charge distribution? How is this important? And I'm going to cite two reasons which make the use of continuous distributions important. And it's more like, because we have to deal with continuous distributions, let's see if we can find a little more meaning as to its application. So one application, I think is the obvious one, is going to be for finding forces. Now, we said the electric field was defined as F over Q, and that oftentimes for convenience we write it as F is equal to Q times the electric field. Now, this representation, this E that we have here, can be from a uniform electric field, as though it's between two parallel plates, or it can be an electric field due to a point charge, in which case the force that you get would be for only a single point in space. So if I have a point charge and it's located right here, well, there's an electric field which is pointing radially inward towards the the electron in this case, and then the force is also going to be pointing parallel to that. But as I get further away, the force gets weaker, and as I get closer, the force gets stronger. And this is a nice, I'll say, symmetric electric field that we see here. But it's not always quite so symmetric when you have a continuous distribution. But this E that we come up with is still going to be valid even if it's not a nice smooth distribution, a nice symmetric distribution of electric field, because we're only focusing in on one point. So our first use is going to be for determining the force on a charged particle. The second use that we have for determining the electric field due to a continuous charge distribution is going to be for determining electric potential. And electric potential, or electric potential difference, is actually very useful in electricity. I would argue it's probably more useful and less academic than just determining the force. So what we're doing here is just a very short preview of what is coming. And the electric potential is equal to minus the integral of E dot ds. And this looks kind of scary, and I guess maybe in some ways it could be. But here's the bigger point. We're trying to find the electric field of a continuous charge distribution, and that would be for some field that's out in the middle of space, wherever it happens to be. But the electric field is not something that's particularly useful to be using. Electric potential is far more practical for determining a lot of things in electricity, and we'll talk about that more whenever we get to electric potential. So anyways, this electric field that we have right here is the same thing that we come up with when we use the continuous charge distributions. So it has a purpose later on, even though right now it may just feel like an exercise in mathematics. But believe me, it's not. We actually have a good use for it. So with all that said, let's go ahead and move on with our discussion. There are a few basic field models that we're going to be looking at when it comes to charge distributions. The first one we're already familiar with, that's going to be point charges. Nothing more needs to be said with that. The second one is going to be, I'm going to call it a long wire or just a wire segment. Okay, and that's, if you had to look at what I'm talking about, it's just a chunk of wire. It could be really, really long. It could be really kind of short, depending on the circumstances. This will also be true for an infinitely long wire. That is what we'll look at with Gauss's law. We'll define just what exactly is meant by an infinitely long wire, because no wire is truly infinitely long. So we'll take a closer look at that when the time is right. We also have a plane, a flat surface, and that could be something like your desktop, or if we're looking at capacitors, that's where this one becomes really important. We need to know, what does that electric field look like? And then the last thing we can look at are charged spheres. And the sphere, basically, as long as you're not right on top of the sphere, it's going to look like a point charge. So that's pretty easy peasy. Now, if there is a key to working with continuous charge distributions, the key is going to be understanding how to work with charge density. And charge density is just like working with mass density. Mass density, we would say, is just mass divided by volume. And we have the same basic thing for charges, except there's 3 different types of charge density, and each one has its own use depending upon the type of density you're looking at. And so you may not be very familiar, or you may not know anything at all about these, but let's go through them. Basically, you get one for each dimension. So what I mean by that is that lambda, which is going to be equal to the total charge divided by the total length. So lambda is equal to Q over L, and this is what we call linear charge density. Now basically what that means is that you have charges which are in a line. And if you were to cut this into chunks, let's just say this is a line of charge. You can cut this line of charge into chunks. If you cut it, well, I guess I probably should have had one more charge in there, but if you cut it right here down the middle, then, well, first of all, the linear charge density here, lambda, is going to be the total charge, which I'm just going to say is the number of dots I have here, is going to be 5 divided by the length L. If I cut it in half, then lambda is going to be equal to 2.5 over 1/2 L, which is still the same thing as 5 over L. If I were to cut this half in, if I were to cut the half in half, then that would be right about here. Then my linear charge density is going to be 1.25 over 1/4 L, which again simplifies down into 5 over L. So this is for a uniform charge density. All of these are going to be for a uniform charge density, which means it's constant. It's like taking a chunk of aluminum, and let's say it's aluminum rod. If you cut the rod in half and you measure the density of that aluminum rod, you still expect it to come out to be whatever aluminum is. And if you cut it into fourths and really tiny chunks, it's the density is always going to be the same because the material hasn't changed. And so is going to be true for our charge densities. So a linear charge density is whenever our charges are stretched only into a line and not across a surface. And sigma is going to be our surface charge density, and that's equal to Q over A. So I take all these charges and I just spread them out over a surface. And again, it's uniform. So no matter how big the chunk is, and no matter where I take the chunk from, I'm always going to have the same density. Now, I wrote area charge density here. I probably should have written surface charge density because let's look at this. This is lambda. It starts with an L, L for linear. This is sigma, starts with an S, S for surface. So it should be relatively easy to remember which one of these goes with which. Ultimately, it doesn't really matter whether you call it lambda, sigma, eta, beta, whatever variable you happen to use to represent your charge density. The most important part is that you understand it's Q over L, Q over A, and then finally, the volume charge density is going to be Q over V, or charge over volume. Strictly speaking, you cannot use Coulomb's law for a continuous charge distribution. And the reason we say that is because if we take the example for our bar of charge, okay, so we got all these charges stretched out in a line, and you want to know what is the electric field at this location in space, or the electric force on a charge. So let's say this is a positively charged particle of plus Q, and it's some distance d away from the end of this rod, and this rod has some amount of charge of also plus Q, but it's going to be a capital Q. So it's a different amount of charge. Large or small doesn't matter. Now the question becomes, if I want to use Coulomb's law, I know that it's F is equal to K QQ over R squared. And if I'm just looking for the electric field, it would be K Q over R squared. But remember that this capital Q is the source charge. So the question becomes, if I want to know what is the force at this location in space, do I put all my charge here on the very end? Do I put all my charge on the other end? Or do I place it somewhere in the middle? Well, if you put all the charge on this end at location 1, then you end up with a force which is much too great, because this has a uniform distribution and my charge is not all located at this point. But Coulomb's law doesn't allow for you to place the only some of the charge here, not strictly speaking, not by itself. And the opposite is true on the other end. If I go to location 2 on the far end, then I end up getting a force which is much too small. So somewhere between these two extremes is going to be the actual location for that point that you could assume all the charges to be. So we get our two extreme values of force. We know our answer has to be somewhere between these two values, whatever that happens to be. And you can't just place it in the middle either. That is something that we did with center of mass, but that's not something that you can just do with your charge, because it's a 1 over r squared relationship. So the further away you get, the less effective the charge is at creating a field at the point you're interested in. So we are going to use Coulomb's law, but we're going to have to adapt it, because basically what we're going to do is we're going to use superposition to add up many chunks of this rod. Now we're going to break this rod up into many chunks. We're going to break it up into an infinite number of chunks, and anytime you have an infinite number of chunks to add up, you're going to use calculus. So when it comes to doing these problems, I'm confident that your calculus skills are razor sharp, that you won't have any issues with the calculus by itself. The real issue is going to be in setting up the problem. That's going to be the most important thing you can do to solving these. You need to make sure that you can identify constants, and you have to accurately identify variables. And when we talk about variables, we're referring to those things that within the context of the problem are changing. And we're going to look at an example of that in just a minute. Constants are going to be anything that don't change within the context of the problem itself. Okay, so let's take a look at the case where we have a bar of charge and the charge is uniformly distributed across the entire length of the bar, and we just want to know what is the electric field out here at point P. So we're just looking for the electric field. Now, Coulomb's law, remember, for point charges we adapted so that E was equal to KQ over R squared. And that's going to be central and fundamental to our understanding of how to do these. So the first thing we have to do is establish a procedure for how we get through this problem. And so the question becomes, what is constant, what is variable? So first, let's identify the things that we actually have to deal with. We have D, we have an L, all right? Now, we also have a Q for the charge, and it's not drawn on here yet, but we also have chunks of charge that we're going to have to deal with. They have a very small width, and they're going to be located at some distance x from the point that we're interested in. So x is also going to be one of those variables that we have to decide. Is it a variable in the context of the problem, or is it going to be a constant in the context of the problem? And the last thing that maybe isn't so obvious in this problem is going to be theta. And you might ask yourself, well, why would we even think about theta? Well, I'm trying to make this more general. What if we had a point that was located right here above the end of the rod? Now we have an electric field which points from this chunk, it points up and to the right. Okay, so I am going to throw theta into this list, but I think it should be obvious that as we go from one chunk to the next all along the way, that theta is going to be equal to a constant. D is a constant because it's not changing as we go from one end of the rod to the other, so this is also equal to a constant. The length of the rod is also equal to a constant. It's not changing size or shape as we move along. Q is going to be a constant. So the thing that's changing in this problem is x. We're going to start at D, and we're going to go to a location D plus L, and so the location of each individual chunk is what's changing. So this is the variable. All right, so let's write E is equal to KQ over R squared. And the first thing I want to mention is that R in this case is going to be equal to x. And the reason that R is equal to x is because R is equal to the square root of x squared plus y squared. And because we don't have anything going on in the y dimension, this goes to 0, and the square root of x squared is just x. Now, this x squared is our variable, so when we get to the calculus part, this is what we need to make sure we're integrating with respect to. Now what we need to do is break this bar up into many small chunks. That way we can apply Coulomb's law to each of the chunks. And so what we get is a small electric field delta E at location P is equal to K times delta Q over x squared. Now if we look at this in the limit, as the chunks begin to get infinitely small, then what we have is that delta E is going to become a dE, and delta Q is going to become a dQ. So let's rewrite this as dE is equal to K dQ over x squared. We know that we have to add up all these chunks, and that's going to make this an integral, because all we have right now is this small differential electric field. So we integrate, and this is going to result in us getting E is equal to, and then I'm going to pull out K because it's a constant, the integral of dQ over x squared. Okay, now let's establish our limits of integration. First of all, even before I do that, dQ is problematic because when we integrate this thing, we said our variable was x. We're going from x is equal to d to x is equal to d plus L. So we can write that in right now, d to d plus L. This integral is set up so that we're integrating with respect to q, but q is a constant in this problem. Now, what you cannot do, this is not an equality. You cannot say that E is equal to K over X times the integral of dQ. This does not work. All right, so what we have to do is find a relationship between Q and X, and we're going to do that here in just a moment. In fact, this is where charge density becomes exceedingly important. Okay, so we have E is equal to the integral of K dQ over x squared going from d to d plus L, and now we want to work on dQ. We got to get dQ to become a dx. And how are we going to do that? Well, this is charge density that we're going to be using, and we know that lambda is equal to Q over L if it's a uniform charge density. We also know that lambda for the whole thing is equal to lambda of the chunk. Lambda for the whole thing is defined as Q over L. Lambda of the chunk is defined as delta Q over delta X. And we said that taken in the limit, the deltas turn into d's for differentials. So we get Q over L is equal to dQ dx. So solving for dq, I get dq is equal to Q over L dx, but Q over L is just lambda. So you have a choice. You can write this as dq is equal to lambda dx, or you can write it as dq is equal to Q over L times dx. And which representation you use is not all that important in those intermediate steps of the problem. Where it becomes important is when you get to the final step where you have to express your answer with the proper variables. And so, for example, on the AP exam, they may give you lambda, but lambda is not an appropriate constant, and it's not a variable of the problem. So most of the time, what's going to happen is you're going to have to make lambda Q over L in order to get it into the proper variables, for what the examiners are looking for. What we get is E is equal to k times the integral of d to d plus L of, now we get to substitute lambda dx for dq, so we get lambda dx over x squared. And now this is something we can integrate. So E is equal to k lambda times the integral of d to d plus L of dx over x squared. So E is equal to k. And now I'm going to make lambda q over L. So that's q over L. The integral of dx over x squared is just going to be 1 over x. And we'll evaluate this from d to d plus L. So E is equal to kq over Lx evaluated from d to d plus L. And I'm not going to do this final evaluation. That's something that's simple enough for you to do. But there is one more point that I want to make, and that is that q, or I'm sorry, not q, k, this constant, is 1 over 4 pi epsilon naught. So for convenience right now with this problem, you can write k, but very, very shortly in the next several videos, we're going to find that it's far better to write k as 1 over 4 pi epsilon naught instead of just k. And so our final answer is going to be q over 4 pi epsilon naught times Lx, and that's evaluated from d to d plus L. Then finally, as a final check, when you substitute these values in, you want to see a couple of things. You want to see that your value falls between the two extremes. Remember, we get the high end extreme on the left end of the bar, the low end extreme on the right end, and so the value you get for the electric field is going to fall somewhere between those two values. The other useful check is to see if you've done everything correctly is take this in the limit as x goes to infinity. Okay, and what you should see is that as you get further and further away, it begins to approximate a point charge.